Hi everyone, I'm Shanti. I'm going to present you my work on classifying restaurants using images. This is done as pattern recognition course at University of Florida. To give an overview of this presentation, I will walk you through the following topics: the project description, use cases of the project, RCNN based architecture, multiple instance learning, system architecture, flowchart, challenges, performance metrics, and the conclusion. So, coming to the project description of my project, people nowadays depend mostly on the reviews of the restaurants in order to classify them. They get lots of information like the atmosphere of the temperature, the type of food it serves, price range, and many more factors. Yelp is one such company that publishes reviews about local businesses. Using the photos of the restaurants submitted by the users, Yelp is challenging Kaglers to design a model that predicts the tags for restaurants automatically with multiple labels. At present, labels for restaurants are selected manually by the Yelp users for submitting a review or posting a picture. But labeling is not mandatory while submitting the review, due to which many of the restaurants are not categorized completely. Our goal is to identify the business attributes based on the photos that correspond to a particular business. So this problem is addressed using the following 9 attributes. So whether it is good for lunch or good for dinner, whether it is taking reservations or not, is that restaurant is expensive, whether it serves alcohol and it has a table service, whether it is good for kids or not. So these are the factors that we are going to consider. Currently, these labels are provided by the community of Yelp. So there are certain challenges that we are going to face in this. Labeling a restaurant may seem straightforward, but the fact that every restaurant has many number of images corresponding to it, and it's highly difficult to figure out which label is corresponding to a particular image. When compared with other image classifications, this presents a unique challenge of classifying multiple images with multiple labels, in contrary to classifying using a single label. So coming to the use cases of my project, user can upload images of a new restaurant that they visit. So when user searches using new business attributes, he or she tend to get more refined results as all the restaurants are assigned attributes automatically. None of the restaurants are left uncategorized. This gives an equal chance for all the restaurants to be displayed in the search results. This makes business head understand the standards of his restaurant such that he or she can improve in that particular business attributes. So coming to the RCNN based architecture, we are using this in order to get the whole overview of the restaurants. So we used object recognition and scene classification technique to identify different objects underlying in the images of the restaurants. Using this information, a classifier is implemented that gives labels to the restaurants. As this picture depicts, the neural network mainly consists of two convolutional layers followed by a pool layer and two globally fully connected layers. So finally, we have added two more convolutional layer and a max pooling layer in order to maximize the number of the mid-level features extracted. The final output is given to the classifier. The classifier can be a softmax classifier or a linear SVM. So the main reason we thought we can do using RNN is it employs the region of interest pooling scheme that allows the reuse of computations from convolutional layers. But there are some problems with this approach. Implementing selective search on the large dataset posed an issue. Our dataset has many to many mappings. That is, multiple images contribute to multiple labels. But the reason that it is not suggestible because it needs the training dataset to be labeled with bounding boxes of each image. In ELK dataset, there are 1/4 million images approximately. All these images are available in raw form and are grouped under respective business IDs. Data in this form is not feasible to train RNN as it requires the training data to be already labeled. So we are using multiple instance learning approach. Multiple instance learning works for this problem as there are multiple images contributing to multiple labels. So different scenarios can be discussed in this case. There are multiple images contributing to one of the labels, one image contributing to one label, one image contributing to multiple labels. So keeping all these problems in mind and all these factors, I chose to work on pre-trained CNN. So the system architecture that I have employed is, firstly, I trained AlexNet CNN using the ImageNet database and thus generated feature vectors for images using this train network. Many feature vectors for each business ID are obtained. My intention is to learn about single instance using multiple labels. So we reduce multiple feature vector into single feature vector by calculating the mean of all the vectors. This results in a single consolidated vector for each business ID. We can solve this using multi-layer SVM classifier. The above generated feature vectors are given as input to the classifier and this classifies images. This will work because the above generated vectors will contain all the important information about each image. The picture explains the architecture that I have implemented and that I have explained so far. The flowchart describes the flow of our project and the implementation steps. The images are provided by the ELP community. They are pre-processed such that the training of CNN happens in an ordered fashion. The photos of particular restaurant are fed into the AlexNet train CNN. So this is the code. And based on the weights learned, the neural network can be changed in future to improve the efficiency in labeling the restaurants. We take the average feature of vector to provide a single vector for each business model. So this is for this. This is given as input to the linear SVM classifier. The linear classifier then generates business attributes related to business ID. So coming to the modules of the project. So input processing module. This is all about the processing of the dataset that we have given. The dataset that we have got is very raw. So directly giving this to the pre-trained CNN doesn't yield good results as some images are available in landscape mode and some in portrait. So to remove the non-uniformity in the testing and training data, all the photos are resized to 227 cross 227 size. These images are fed later to the next modules. Coming to the CNN training module. The main purpose of using CNN is this approach is to extract all the possible objects from the images. In order to get good results with high accuracy, we need to identify all kinds of objects. This can be achieved by training the neural network with large datasets, so we choose ImageNet dataset for this. Adapter module. The main purpose of this module is to generate consolidated feature vector for particular business ID. This acts as adapter layer between the output of CNN module and input to the multi-class classifier module. Multi-class classifier. We trained SVM classifier with maximum margin using the on-rest technique. This classifier outputs a hyperplane for each label which separates positive examples from negative examples. By using single hyperplane for each label, we are reducing the problem to multiple instances of binary classifiers. So the challenges that we have to face, we need to come up with a way to map these multiple images with multiple business attributes and consolidated the feature vector in an appropriate way that choose a metric that trains the data the best. So for the performance metrics, the mean F1 score is the performance metric measure for ELP competition. So the mean F1 score can be calculated using the given formula. Base F1 score that we have got by taking each attribute randomly with equal probability for each image, we have estimated the F1 score for this most naive model. So the result we have got is 0.46. And there are several experiments conducted to achieve high F1 score. If F1 score is high, the more appropriate the labels are given to the images. This is explained in the next slides. Calculating the FC8. Calculating the F1 score using FC8 layer. So in neural network, the last three fully connected layers are named as FC6, FC7, FC8 respectively. Initially, the data is extracted from SC8 as it is readable by humans. Each extracted vector has 1000 dimensions and each value is the probability of each business label present in the input image. Results using the FC7 layer. Now the data is extracted from FC7 layer. The extracted feature vector has so many dimensions when compared to that of FC8. This is not understandable like FC8 layer data, but there is a little increment in F1 score as we are using higher dimensions. The data extracted from the FC6 layer led to the reduced F1 score than FC7 as feature vector extracted at FC6 did not learn more feature values than FC7 feature vector. We also tried using feature vectors from different spaces, that is one feature vector from FC6 and one from FC7. But in order to calculate the F1 score, we need the feature vectors to be in the same space. This is the reason I normalized the both vectors to get the best result. So before concluding, I will give the list of findings through this project. As the ELP Kaggle dataset is very large, I observed that training the neural network for multiple labels is complex and needs high computation power. So, I used a pre-trained convolutional neural network, that is AlexNet, on image database along with multiple label SVM classifier. I recorded a F1 score of 0.78 approximately. In order to learn more about the behavior of the model, an analysis is made on the performance of every label. Thank you.